So hello to everyone who's watching on YouTube. I guess we'll get started in like 10 minutes, just waiting for a few people to join the session in person. So yeah, if no one joins, nonetheless, we'll get started in like 10 minutes. Till then, I'll just mute myself. Okay, so since no one has joined the session in person yet, I guess we can get started nonetheless. So first of all, hello to everyone who's watching on YouTube. Just to reintroduce myself, I'm Lakshya Saggi, the problem-solving TA for the Monday 6 to 8 p.m. sessions, and I believe this will be our 11th session now. And in this session, we'll be talking about the topics covered in the week 11, which were more or less about continuation of uh, which today's in this week's lectures were mostly continuation of previous week where we were talking about like embedding graph embeddings. So this week also we'll discuss some methods in detail like random walks or some other methods which we'll come to in a while. And yeah, we'll be discussing those methods for graph embeddings in detail uh, in this week. And then, like always, the as I always say, these sessions are not a substitute for the lectures. So uh, while discussing questions or while give first of all, like I'll be giving summary of the lectures of this week, of the topics covered in this week, and I'll be assuming that you guys have gone through the lecture videos first. So I'll not be discussing everything in detail as I obviously can't cover everything in 2 hours what was covered over the whole week. So yeah, so I'll be assuming that you guys have seen the lecture videos and we'll be discussing on a much higher level. We'll be discussing everything on a much higher level than what has been discussed in the lectures. So without further ado, I guess we can get started. Let me just share my screen, guys. Yeah. Yeah. So this is week 11 and yeah, so we have a bunch of so first we have like some important notes from the lectures. Uh, so we'll be discussing the summary of what was covered in the lectures, and then we have a bunch of questions based on those lectures. So I believe today's session will not be too long as yeah, as has been the case in this course. Usually what we have is we have a lot of like breadth covered in topics and not too much depth in each topic. Like some topics have depth involved, but most of the topics are are like taught in a more of a breadth manner, so that you guys can uh, go into depth or read up things on your own. So this week also, I think. Won't go into too much of depth. But we went like somewhat like some maths and all was covered in the lecture, at least for this week's lectures. But I won't be going into all that. Uh, and if you want to revisit the math of the models involved in this week, you are free to like watch the lecture videos again. So yeah. So other than that, I think not a lot of topics were discussed. So this probably won't be a very long session. And like, if there was someone in the chat who had some doubts, then I could have answered those doubts. But since no one is present in person in the meeting, I guess uh, it is what it is, and we'll just discuss what I have prepared for now. So, in this week's lecture, the first in the initial lectures of this week, we first started off with this line network embedding model. Sorry, guys. So line is large scale information network embedding, and this was a breakthrough graph embedding result presented around 2015. And the high level idea of why is this line architecture important in context of social network analysis is can be seen from the abstract from the highlighted part. So prior to this work, most graph embedding models did not scale for real world information networks, which contain millions of nodes. So usually, like for very large networks, prior to this line model, there did not exist many networks which could extend to like millions of nodes. However, this line model could extend for like arbitrary types of information networks and very large networks also, whether the networks are undirected, directed, weighted, or unweighted. This line network would work for all of those. So that's why. this line network was an important breakthrough. And like the ideas involved, okay, maybe the math involved is a bit tricky, and some of that math was discussed in the lectures, but we'll just be discussing the high level idea of the model, and that is really like not too hard. The high level idea is the intuition behind these models are like some ideas which we have already covered in the initial weeks of the lectures, and we can come to that later on, and you can identify it yourself. But first of all, so yeah, so let's look at this figure first for some motivation behind the line network. So consider maybe all the edges are like undirected as well as unweighted. And let's say this is an information network where there are some nodes and they have some like undirected and weighted edges between them. Then like yeah, for now like so edges can be undirected, directed or weighted. But for now let's just assume the simplest graph, undirected and unweighted. So the idea behind these line networks is Uh, vertices 6 and 7. So these two vertices, let's say the vertices 6 and 7. So they are directly connected by an edge. Or maybe like, let's say they are connected by multiple edges. So if these vertices are, connected by connected by these edges, then this means that uh, uh, these should be like, since these have like a direct connection and a very strong direct connection, so line network just says that okay, so if two vertices are connected directly by a very strong edge, then they should be like close to each other in the graph embedding also. So even if we are embedding the no vertices in a low dimensional space, still like these vertices should be close to each other because they have a direct edge which is very strong edge. And similarly, the second idea behind line network is okay, so all the vertices which have very strong ties should definitely be close to each other, but some other vertices should also be close to each other, which are the vertices which share similar neighbors. So consider the vertices 5 and 6 here. So for both vertices 5 and 6, the neighborhood set is like at least these 1, 2, 3, 4. So there are four vertices which are common neighbors between vertices 5 and 6. So vertices 5 and 6 are quite similar to each other since they share a very large neighborhood. And that's why maybe vertices 5 and 6 are very similar to each other. So these two vertices should also be close to each other in the final graph embedding. So these two are the principal ideas involved in a line network. I know that these high level intuitions, both of these intuitions have previously been covered in like in even in the initial lectures for this course also, that two nodes can be close if they have a direct edge which is very strong, or two nodes can be close if they have like, so these kinds of ideas were discussed in community detection also, and two nodes can be like close to each other if they have a very similar neighborhood. So that's why like all these vertices, so 5 and 6 should be close in the graph embedding because they share a very large neighborhood. Similarly, 6 and 7 should be close in the graph embedding because they share very strong tie. So yeah. So these two are the high level ideas, are the underlying ideas behind the line network. And coming to somewhat of the math involved. So okay, maybe. So this idea of vertices being close if they have a strong edge between them is called like first order proximity. So the authors in this line network call this first order proximity. And the idea of the vertices being close if they have a large common neighborhood is called second order proximity. So yeah. So with respect to first order proximity, uh, the authors define some probability distribution between any two vertices Vi and Vj which share an edge. So the authors define a joint probability distribution, which is like a probability that Vi and Vj occur is equal to like 1 divided by 1 plus like e raised to the power minus Ui transpose Uj. So Ui vectors and Uj vectors are the vectors corresponding to the graph embedding. So these are the vectors which we have to find out, obviously. And the authors say that, okay, so if these Ui and Ujs are the vectors, then let's say like the probability of V and Vj occurring is something like this. Yeah. And we can define something like a weighted version also. And then to preserve first order proximity, a straightforward way to mean is to minimize the following objective function, which is like a uh, distance between uh, two probability distributions, P1 cap sum and P1. So something like that. And yeah, so the distance can be, so distance between probability distributions can be done by maybe uh, like any distance metric which you can define over probability distributions, maybe like a KL divergence or something like that. But the high level idea is okay. So maybe let's not get into all of this, but the high level idea is okay, like if the UI and UJ vectors are like so the high level idea is like if UI and this UJ vector, both of these are, let's say, similar to each other, like or like very close to each other, as we say, then what happens is this value, like this UI dot UJ value is very large, then this negative of UI dot UJ value becomes very small, and then this whole value becomes smaller if UI dot UJ becomes large. And then if the denominator becomes smaller, then the whole actually the fraction actually becomes larger. So, so what this essentially says is larger is this dot product, ui dot uj dot product, larger is this joint probability distribution between vertices vi and vj. And this joint probability distribution essentially states that like larger is this probability of vi and vj. This means that there's a higher chance that vi and vj share an edge between them. So if like let's say these ui and uj vectors are very similar to each other, then this just means that if ui and uj vectors are similar to each other, then this means that this p1 value, this p1 vi vj value is very large. And what this means is like there's a higher chance that vi and vj have an edge between them. Or like you can say it vice versa also, that if vi and vj have an edge between them, then this value should be larger. So note that, so one thing to note here is, okay, I just want to clarify this. Yeah. So as we said in the graph embedding, like vertices should be placed closely in the vector spaces. So what do we mean by closely actually in these embedding spaces? So closely can be thought of as like maybe a distance metric, but here like we are not referring to closeness with respect to distance metric, but rather the closeness with respect to like the dot product between any two vectors. Like higher is the dot product, or like higher is the cosine of the angle between the two vectors. So this we also discussed in previous week, that distance metric between vectors does not need to be an L2 norm or something. It can also be like this dot product thing also. So yeah. So essentially this equation defines the probability distribution over the space of V cross V, and the empirical probability distribution, which we know already, is like Wij divided by W. Like, so this is the probability distribution which we are expressing in terms of some parameters, and this is the distribution which we know actually exists. Like, so there is something we know that between any two edges, any two vertices I and j, an edge of weight Wij exists between those two nodes, and the probability that then the what that uh, there is an edge between I and j empirically can be just written as Wij divided by capital W, where capital W is just weights, summation of weights over all edges. Then to preserve first order proximity, a straightforward way is to minimize. So what we want to say is, okay, so our distribution in terms of parameters should be as close to the empirical distribution which we observe. So what one can do is minimize the distance between the empirical distribution and our parameterized distribution. And yeah, and the distance can be uh, whatever distance metric you want to take between the probability distribution. So it's up to you. Usually, I think a lot of people tend to take it as scale divergence or something like that, but it's up to you. So yeah, okay. And then maybe so we won't go into a lot of math, but like that seems so. So what is line with second order proximity? So this was just, so here in the first order proximity we were just looking at edges, right? Edges, I, J, and so on. So we did not look at like the common neighborhood thing. So that comes into picture in the second order proximity. So second order proximity assumes the vertices sharing many connections to other vertices are similar to each other. And here okay, so here each vertex should be treated as a specific so each vertex is treated as a vertex, but is also treated as a specific context. And what do we mean here? So uh, so so what we are referring to here as context is is similar to what we are referring to as neighborhood. So in the actual graph, we are saying that vertices with similar neighborhood are similar to each other. But here, if we are referring to it in some formal terms, we are saying that vertices which have similar distributions over the context are assumed to be similar, and context is just similar to the neighborhood which we define. So in this line with second order proximity, each vertex plays two roles. It's the vertex itself, and it acts as a specific context to other vertices. And so we introduce two vectors for each of the vertex. Like one vector represents the vertex itself, and second vector represents the context vector for that vertex. And then one can define probabilities of context with respect to certain vertices and so on. So let's not get into that. But yeah, but the high level idea here is this only, that in line with second order proximity, we tend to say that vertices in similar neighborhood are closer to each other. And to model this mathematically, we say that okay, each vertex has two roles. One is that vertex being embedded itself, and the second role it plays is it acts as a context to some other vertices. And then we try to again try to find out some empirical distribution and this parameter distribution and try to minimize the distance between the distribution or something like that. So if you want to go into a bit of depth, you can look up the original line paper, or yeah, some of these things were discussed a bit more in depth in the lectures. But still, if you want to get the full picture, much then it's much more advisable to just directly look at this line research paper itself. And it's not a really big paper, I believe. So yeah. Okay then. So we have discussed this line network. So this is yeah, yeah. But then so this line network involves a lot of mathematical formulas and everything, and looking at graph structures. So even though it's extendable, it's not very fast. Like if you want to have, let's say, so to model this line network and optimizing and everything, you actually need to look at the whole graph. And then you need to introduce parameters for all pairs of vertices and so on. So even though it's somewhat faster than some other models, but it's still not the absolute fastest. So it gives very good results, this line network, but it's not very fast. So if one wants to trade off maybe some more accuracy, we can let go of a bit of more accuracy, but we want a faster algorithm for graph embeddings, then usually what people turn towards are these random walk based methods. So okay, I'll have to mute myself for a second, guys. Sorry for this. Sorry for that. So usually when one wants a faster algorithm for graph embeddings, people tend to use random walk-based methods. And what's the high-level idea underlying these random walk-based methods? So what one does is, okay, maybe we have to find uh, graph, let's say embeddings for each of the nodes. What one can do is maybe like take each of the node as some kind of a source, and then let's just start doing some random walks from that node. And note that what these random walks do is they kind of reveal the structure of the graph to some extent. So that suppose you don't want to explore the whole graph, but you want to look at some kind of a local neighborhood or what's the structure in the local neighborhood without exploring the whole graph. You don't want to explore the whole graph because you want to save on time. You want to be even more efficient than looking at the whole graph. Like then you can just do random walks and see uh, like what's the structure of the graph around like some specific node, and these reveal some info. These random walks, like doing these random walks multiple times from each vertex, reveals a lot of it turns out like this reveals a lot of information about uh, what could be a good graph embedding and so on. So the idea is like one uses random walks to learn the low dimensional latent embedding of each node, and this captures the local neighborhood and structure of a node by performing enough random walks with a seed node as the starting node. So seed node is nothing but the what we are calling the starting node. And output of multi. So note that just doing one random walk is never enough because random walks are probabilistic in nature, and if you want to have like good probability results, usually it's nice to run the experiment multiple times. So random walk can be thought of as some kind of an experiment. And if you run the experiment multiple times, then uh, you can get far more accurate observations. So that's why one should do random walks multiple times. So how many times is another a question for another day? Like you can show like using math like some x number of random walks is sufficient to get results of good probability and so on. And note that these random walks based methods tend to be fast. So first of all, because like so suppose you want to do random walk from you want to know the structure of the graph around a certain node V. Then you will take that certain node V as the starting node and perform a random walk from there. So note that and note that these random walks. So suppose you want to perform a random walk from a vertex V, and then you want to perform a random walk from a vertex W. So note that these two random walks are completely independent of each other. So multiple random walks on different seed nodes can be computed in parallel. If you have multiple processors, you don't need to serialize these random walks that first you'll perform a random walk on V, then only you can perform a random walk on W from W. Like you can perform these random walks simultaneously if you have a lot of processors available. And so this is why like this parallelization helps in making the random walks faster, these random walk-based methods faster. And another thing is if a change occurs in some network, then only the affected nodes need to be recomputed. So as I said, like so if you want to compute like some local structure around some specific nodes, then if some nodes are affected, then only the random walks around those affected nodes need to be recomputed. You do not need to recompute everything in the graph from scratch. So there is a bit, so always like this kind of so these kinds of methods which are a bit more local. So the previous line method was more global in nature because it looked at the whole graph and formed this probability distribution. These random walk based methods, although they are not entirely local, like they just don't look at the vertex and its neighborhood, but they are like more local than the line network method because they look at like maybe certain neighborhood, not the whole neighborhood, but some certain neighborhood of a node. And that's why like you don't need to recompute everything from scratch. If in case of certain failures, you just need to compute these random walks for the affected nodes. So this is the high level idea behind random walk based methods. Like till now, we have not discussed any like specific algorithms or something. So usually there are two uh, algorithms which are quite popular in these random walk based methods, which are like deep walk and node to wig. So what is deep work first of all? So deep work, what deep work does is it uses uniform random walks based on a seed node, aiming to identify local neighborhood of the node and capturing local community information. So here you just do a uniform random walk, like we already know what are uniform random walks, that you move to any neighbor uniformly randomly from a node. And how is this random walk generated? Maybe let's just see. So a seed vertex is sampled, the starting vertex, and then a set of multiple random walks based upon the seed vertex are computed. Random walks are uniform, and note that in this deep walk method, these random walks are fixed length. So this is very specific to this deep walk method. That deep walk method says, okay, the random walks which we'll be doing will have these fixed lengths. Uh, so there will be a fixed stopping length that, okay, when you traverse, let's say 10 edges or 11 edges or something, then you'll stop your random walk. And yeah, so, and the length of the random walk could be set randomly. So although the random walks are uniform and they are fixed length, like what should be the length is can be fixed randomly. Like you choose a random length and you say that, okay, all the random walks which I'll now be doing will be uh, equal, will have this length L. And we also, like, usually what we do in these random restarts and everything, like we have already discussed, like page ranks with random restarts. So these random walks also have these random restarts that a teleport probability could be assigned to random walks. That okay, one might teleport, like you just don't need to like always go into this random walk, uh, like uh, random walk like from one node to one of its neighbors, but maybe one can teleport to one of the other nodes also. So this kind of thing has already been discussed in the context of like computing page ranks, if you remember. So yeah. And how does one update the parameters? So note that the parameters are like maybe these lengths, and then the embeddings. Basically, the main parameters which one wants to compute are the embedding vectors for the graph nodes. So for this, at least in this deep work method, is done using skip-gram language model. So we discuss briefly like what these skip-gram models are uh, in the previous session. And the skip-gram model is used to maximize the co-occurrence probability among the nodes. So the high-level idea is, okay, like you see like uh, in the random walk, let's say from a certain vertex V, which, so suppose we perform 10 random walks from the vertex V, then let's say we see like, let's say we find out like what are the most frequent vertices appearing in the random walk of V. Then we can find out those things and we can use that information in our skip-gram model. And then we can have some kind of a probability attached to it and yeah, minimize that probability. So again, this is on a high level. We are not going deep into the math of it, but yeah, this is the high level idea. Yeah. And yeah, for learning these kinds of distributions, different classifiers could be used, and at least the original architecture the paper which proposes for use hierarchical softmax. So let's not get into what is hierarchical softmax and everything, but just note that like the softmax function is this. So you may have seen come across this softmax function in the context of neural networks or something. So this is one of the activation functions which is usually used. So suppose there is a vector x of dimension n in dimension n. So then like x has x coordinate n coordinates x1 till xn. Then the softmax of x is just given by this vector, like e raised to the power x1, e raised to the power x2 till e raised to the power xn transpose. So the first coordinate is e raised to the power x1. Second coordinate of this n-dimensional vector is e raised to the power x2 till nth coordinate is e raised to the power xn. And this is normalized by like summing over like e to the xi over I from 1 to I. So let's solve. So x is a n-dimensional vector and softmax of x is also n-dimensional vector. You can see here that this is an n-dimensional vector. The first coordinate is e raised to the power x1, second coordinate is e raised to the power x2, and so on. So maybe I'll just add the other. No. max of x. If x is an n-dimensional vector, then softmax of x is also an n-dimensional vector. So yeah, just a note, not a very hard thing, but yeah, just a technical note. Like, just want to I want to wonder that some might get confused and see this. Okay, like because this has not been specified in the lecture like that. This is a product, but notice this is not a product of e raised to power x1 and e raised to power x2 till e raised to power x. So this is an n-dimensional vector whose first coordinate is e raised to the power x1, second coordinate is e raised to power x2, and nth coordinate is e raised to power x. So yeah, so this is not a product, but rather like a vector with n coordinates. So yeah, okay. Then comes a mm, so like moving on from this deep walk. So uh, now that one can perform random so why does one just always need to perform some kind of a random walk only and that of a fixed length? So so one can use maybe some existing graph idea or graph algorithmic ideas to get something better, to get a better idea of like what the neighborhood looks like and everything. So uh, on a high level, so note that first, like the relevant graph algorithm. So what we are right now doing is we are trying to traverse the like in random walks or something. We are trying to traverse the graph from starting from a certain node, so that we can get more information about the structure of the graph, right? And so there are existing algorithms. If you have done algorithms or data structures course at any point of time, you must have come across BFS and DFS. So breadth first search and depth first search on graphs. So these algorithms already exist where you start from a vertex and you try to explore the structure of the graph and try to start exploring the graph. And these algorithms are fundamentally different. Like as what breadth first search does is, as the name suggests, it tries to uh, maximize the number of nodes found at each level. Okay, like it might be a confusing, but on a very high level, uh, like what breadth first search does is like it try so whenever you are doing a kind of a walk, so you can say like how many levels have you discovered in the walk. So what breadth first search does is it tries to maximize like it tries to maximize or go in breadth as much as possible. Whereas what depth first search does is, okay, it picks a node and it tries to go as deep as possible with respect to that node, as the name suggests. Like, uh, I'm just giving a very high level idea of what these are doing, but like, okay, maybe you guys may be already familiar, but still like just giving a description, like a formal description of what BFS and DFS are. So in BFS, actually what we are doing is all the kth proximity neighbors of a node are visited before proceeding to k plus 1th proximity neighbors. So as I already said, like so starting from V naught, you go to the you first cover all the vertices which are direct neighbors of V naught, and only then you go to the remaining vertices. Like suppose direct neighbors of V naught are these V1 till V6. After that, you if you're doing a depth search, what you will end up doing is after that you will discover uh, the direct neighbors of these vertices, any of the vertices V1 to V6. So like V7 is a direct neighbor. So in breadth first search, what happens is uh, first you discover V0, then you discover these vertices in some order, and after discovering these vertices, you discover this vertex V7, and after discovering V7, you will discover these two vertices V8 and V9. And after that, you will discover the vertices V10 and V11, and then you will discover the vertex V12. So this is what you will discover in breadth first search. Whereas what you will do in depth first search, all the neighbors of the currently visiting node in level are explored before proceeding to the next node from that level. So, so what this means is, as soon as you encounter a node, if it's not visited, you instantly move on to some unvisited neighbor of that node. and you keep doing this as much as possible, as far as you can do it. So for example, suppose you're starting from V naught, so as these dashed edges. So note that the solid edges present the BFS walk, uh, BFS search, the first step of BFS search, and let's say this dashed edge presents a example of a DFS search. So for example, like so first you take V naught and then you pick the neighbor, let's say V6. So and this is unvisited, then you visit this V6. Then you take another neighbor of V6 which is unvisited. So let's say you take V7, so you move here. Then you move here, which is V9. Then you move to V10. Then you move to V12. Then you move to V11. And V11 also has an unvisited neighbor, which is V8. So then you move to V8. Then you try to move to V7. Okay, but V7 has already been discovered, so you cannot move to V7. So at least this part of the search ends here. Like so you backtrack. So you have discovered V8 and you have already discovered V7, so you backtrack. You move to V11, you already discovered V11 also, V12, V10, V9, V8, V9, V7. But note that now V7, when you backtrack to V7, so first your DFS search proceeds like this, it proceeds in this manner. And then it sees, okay, on backtracking that V7 also had another unexplored neighbor. So now we move to this from V7 to V2. So first you proceed and you discover these, and then from V7 you discover another vertex which is V2. So you move to V2, and then V2 has an undiscovered neighbor which is V1. So you move to V1, then you move to V3, then you move to V4, then you move to V5, and voila, you have discovered all the nodes in the graph. So yeah, so this would be an execution of BFS search on this graph, if it makes a bit of sense. Okay, so why are we discussing these BFS and DFS? So the idea is that maybe we can combine these BFS and DFS ideas, because random walks are also we are also doing random walks to discover structure in the graph, and BFS and DFS algorithms already exist, which helps us identify the structure of the graph around the vertex. So maybe we can merge these two concepts together and come up with some better algorithms which provide us more insights into graph structures. And this is precisely what the second algorithm, random walk based algorithm, noc25 does. So, mhm. So what we can do in this noc25 algorithm is, so this noc25 algorithm, what it does is it expands upon the idea of deep walk. Uh, this deep walk just used, as I already said, just these random walks of certain length. And note that random walks conducted in noc25 are biased. So here in noc25, maybe let's not get into the mathematical details a lot, but high level idea is one can introduce two further parameters in the algorithm, which are these parameters P and Q. And these P and Qs would kind of so what these P and Q will do is they'll bias a random walk. Like suppose what you want to do is at any point of time in a random walk. So in the deep walk method, we were just choosing a neighbor uniformly at random. But as we have seen in page rank also, sometimes what we need to do is, okay, we need to assign some more weightage to one of the neighbors that uh, one should have a higher chance of moving to some neighbor rather than some other neighbor or something. So these parameters P and Q, what they help us in is maybe biasing our random walk. So yeah, so no, so the deep walk wasn't biased, but in this noc25 algorithm, the random walk we can try to bias using these parameters P and Q. And maybe like without getting the math, the high level idea of what these parameters P and Q intuitively represent is like, so there are these two parameters. So this P is usually referred to as return parameter. And what this does is determines how far the random node is to explore from the source node. So what essentially happens is a high value of P indicates that random walker is more likely to move away from the source node. And the in out parameter Q says that it guides the random walker between whether the one should go to inward nodes or outward nodes. So if Q is less than 1, then walker is more biased to move away from T. So from a node, a walker is biased to move away from T. So like it's more like a DFS. Like if you are doing, let's say, random walk from the node T, then like if you are moving away from T, then you're going more into the depth. That's why it's more like DFS if Q is less than 1. And if Q is greater than 1, then uh, the walker is more likely to move inwards or towards T. So it tends to stay nearer to T as much as possible. And that's why it's more like a BFS. And similarly, like high value of P also indicates that random walk is more likely to walk away from the source node. So moving away means it's more like a DFS rather than a BFS. So yeah, a high value of a return parameter or a low value of a in-out parameter makes the walk more like a DFS, and the other case makes the walks more like a BFS. And these are just uh, mathematical. Uh, so actually, like how do we mathematically model this phenomena? Like we have some parameters, and let's say we want to make the algorithm biased towards, let's say, moving away from a node, or moving like a DFS or moving like a BFS. So one can actually like so rather than having like uniform probability of moving to any node from a given node, uh, what one can try to do is assign different probabilities to different edges, different outgoing edges of a node, and these edges can be given probabilities uh, using essentially the distances. Like so, let's say you are starting from a source node T. Uh, Suppose you are starting your random walk from source node T, then uh, what one can do is, okay, if you want your random walk to be more like a DFS, then at any node V, you want to give more probability to the edges which are moving away, which are taking you further away from T. So if you are at a vertex V, then you want to move uh, further away from T, then you want to assign high probability of taking the edges which take you further away from T. Whereas if you want to make the walk more like a BFS, you want to take those edges first, which are which take you nearer to T, which keep you nearer to T. And that's the high level idea. And these these probabilities can be defined using these parameters P and Q. Uh, yeah. And like this is really not too difficult. So like so the probabilities which you will be using for, like suppose you are at a node V, then for an outgoing edge from V, the edge V comma X, you will have something like a parameter alpha P Q T comma X multiplied by the weight between V and X. So essentially this alpha P Q T comma X is the main parameter whose value is decided using P's and Q's and the distances. So note that if distance between T and X is 0, uh, then the value of this parameter is set to 1 by P. If the distance between T and X is 1, then this is set to 1, and yeah, if the distance between T and X is 2, then it's set to 1 by Q. And you can like work this out, like it's not too hard. It was also covered in the lectures that these kinds of putting these kinds of values corresponds to these observations. Like if you increase P, then it's likely that you will be moving further away from the source node. Similarly, if you increase Q, you will be moving further towards the source node, and so on. So yeah, okay then. And yeah, and you can like, since these P's and Q's are hyperparameters, you can just try out multiple parameters and see like what kind of parameters gives you the best kind of walks or the best kind of results. So yeah, okay then maybe we can move on to the next model. Like again, this is also a high level model, which is graph convolution networks. So what are these graph convolutional networks? Uh, on a very high level, so Uh, if you have, so this was discussed in lectures also, but if you are familiar with message passing interfaces, so what you can think of graphs as being like, so in graphs, like every node is a like, let's say, an information node, and the information, or let's say the message, is being passed around in the graph through its edges, right? So essentially, like this kind of thing is also done in computing page ranks also. Like every node is kind of an information node, and you're passing the information through the edges. So let's say the information which we're talking about is the node embedding itself. So, so essentially, like this graph convolutional networks view the graph as a, like, let's say, uh, mm, uh, message passing kind of network, where like the message to be sent is like the embeddings of the nodes. So suppose every node has its own embedding, then what happens is for every node, you send your own embedding to all of the neighbors, and you receive the embedding from the neighbors, and you try to aggregate those embedding. So this is very similar in spirit to like what you do in page ranks also. In page ranks also, the underlying idea is, okay, you have, like, if you remember what we discussed in page rank, that every page had like uh, some kind of a probability associated to it, and then like based on those, like, or let's say not probabilities but rather importances, and based on those importances, you tend to update the importance of all the pages, like from with respect, like from the incoming importances of pages or something like that. So formulation for graph convolution network is like, okay, so for a vertex v, if you are computing the vector hv, which is like the embedding of the vertex v, and you are in the, like, let's say, so this is an iterative algorithm, and you can decide by yourself like how many iterations you need to do. The more the iterations, the more accurate are the result. But let's say the embedding of v in the kth iteration will just be equal to like some uh, some attenuating factor w raised to the power k minus 1. And so this is like just attenuating factor, like it tries to dampen what has been like discussed in the thing. So just so this w is just a dampening factor, so that like the observations of previous iterations play lesser role than the observations in the latest iteration. So this w is like that important, but the main idea is this part, that okay, what you do is for every uh, every neighbor of v, for every neighbor of this vertex v, for every neighbor u of this vertex v, you take the embedding of u obtained in the k minus 1th iteration, and you try to sum those up. You try to sum all of those up, maybe with respect to certain weights or something, and like you take the average essentially, since this is like divided by n of v, like the number of neighbors. So essentially what you're trying to do is, okay, like this aggregation function can be something different also in graph convolution networks. Here we are just doing a very simple aggregation function, which is just taking averages. And then you append like the existing embedding, which was like hv of k minus 1. So initially, let's say you have embeddings for all the vertices in the k minus 1th step, at the end of k minus 1th iteration. From these, how do you compute embeddings at the end of kth iteration? So what you tend to do is this kind of thing. So in to the embedding obtained in the k minus 1th iteration, you just add the average of the embeddings obtained in the average of the embeddings of the neighbors of the vertex v. And when you do this, like it's you obtain the embedding in the kth iteration. So this is like not really very difficult. It's just like saying that, okay, you have, like, if you think of these embeddings as messages, then what's happening is so V is at the kth step, V is receiving maybe messages from like all of its neighbors, the all the messages which these neighbors received in like k minus 1 iteration, and kind of aggregating them with respect to some function, and then it's appending it to the message which we already had. So yeah. So this aggregation function is like, so here we are taking average. It's a very like naive function, but you can get some further sophisticated functions which maybe can perform better in the graph convolution networks, which can give better embeddings and so on. And the HV0 are essentially the node features. So here like HV0 will be something which will be the initial embeddings which we need to define. and these are essentially the node features for any given graph. So yeah, and then one can have like variations of these graph convolution networks, like uh, like relational graph convolution network, which is also called RGCN. So, and RGCN is like usually useful when the graphs are heterogeneous, or let's say the graphs have some attributes also. Like, uh, so the key idea here is to learn different matrices for different kinds of edges. So knowledge graphs are heterogeneous triples where R is the relation and these relations are non-homogeneous. And then like essentially now what you have to do is in these embeddings, like since these relations are non-homogeneous, you just need to treat these relations separately. Like you can have this W factor, a different W factor for all of the relations and like sum over all the relations. So not really very hard, like it's just a straightforward extension of this idea. So I hope this makes sense. And similarly, so another variation of graph convolution networks is graph attention networks. So attention has somewhat been discussed previously in the, I think last week or something. Like attention is something in neural networks where, or like maybe in networks where you want to like memorize some of the past which has been done. Because uh, some of the past may be network relevant with respect to the present. So in many cases, it is better to give more weight to more influential nodes, and this importance is often called attention, like giving more weight to some more important things. So like this was discussed in previously also, and this is not possible with vanilla graph convolution networks, where we give equal weight to neighbors of any node. So here what we do is, so in graph attention network, like I already said, like you can have this aggregation function as a more sophisticated function, and this is what is being done here. Like, uh, so you have a like rather than just taking a simple average of messages received from all the nodes, you are doing a bit of a weighted average, where the weighted average is uh, where the weights with respect to each of the neighbors is like this alpha UV weight. So whatever these weights are, you're using these weights to aggregate all the messages or all the embeddings received from like the k minus one iteration from the neighbors and appending it to the k minus one embedding. And this is your final output. And now note that there is a further complication in this network, like other than just these H's, you also need to know these parameter alphas. So what one can do is obviously like one can just simply pick these alpha parameters. And yeah, like initially we have these alpha parameters as one. Like in the vanilla GCN, you have these alpha parameters as one. But note that fixing these alpha parameters to be some specific things is again like a very bad way to go about things. If you want to identify influential nodes, like you currently in the starting you don't have any information about what nodes are influential and what nodes are not influential. So if you just set up these parameters, these alpha parameters arbitrarily, you might not be giving appropriate weightage to the more influential nodes, or not giving weightage to like uh, yeah, you can give weightage the wrong way. So that's why another thing which usually needs to be done here is like learning this attention alpha. And this attention alpha parameters also get updated at every iteration. So yeah. So because these attention alpha parameters are very important because these are what describe like how much weightage do you want to give to each node, or how much influence do you want to give to each node. So that's why one needs to learn these parameters also. So in these graph attention networks, so there are two things going on in parallel. So you are updating your embeddings as you move along in the iteration. But as you move along the iterations, you're also updating these attention parameters. Yeah. So essentially these attention parameters influence the iterations, the embeddings observed through iterations. And note that the embedding which you observe, which you calculate at any iteration, will also influence the attention parameter. So note that it's a cyclic dependence actually. Like uh, like uh, your parameter alpha actually influence these h values, and these h values actually influence the alpha values when you're learning these alphas. So yeah, just a cool thing to note. Maybe I'll just put this as a note also. In attention networks, the alpha parameters depend on the h values, and the h values depend on the alpha. Yeah, or maybe learning of alpha parameter depend on h value, and the calculation of h values depends on the alpha parameters. Yeah, just a cool thing to note. Okay, so if this makes sense, I guess this was the yeah, only this was what I wanted to discuss from, at least from the lectures part, the summary part. So there was not a lot of things which we had to discuss from the lectures, but yeah. So some of the math, I skipped a lot of the math involved, but you guys can actually revisit the lectures, or you can see the references which have been discussed in the lectures to actually go through this math in detail. Yeah. So for now, this is what I had to discuss for at least uh, the revising the lectures part, and then now let's come to some of the questions related to these things. Okay, then. So the first question is, so I would have loved some of you again, like I would have loved. Okay, so Karpagam has actually joined. Oh, so hi Karpagam, I actually did not realize that you had joined the session. So did you join a long while ago, or did you just join? Like, sorry, I did not. Uh, I did not see like who's in the session or not. Okay, okay. So, so Karpagam, maybe like you can uh, watch the recording of the session, or if you have doubts, like if you have some any specific doubts on the lectures, you can ask me right now. So what I briefly discussed, at least till now, was like summarizing whatever discussed in this week. So firstly, I discussed what are line networks, and in these line networks, the two important things are these first order proximity, the definition of these first order proximities and second order proximities. So we discussed those, and then we discussed some random walk-based methods, the high-level idea underlying in the underlying random walk-based method, and in that we use like we discussed this deep walk algorithm. Then we discussed what are BFS and DFS, and how this node to vec algorithm uses BFS versus DFS idea. And then we discussed some on a high level, like what are these graph convolution networks and their variations like RGCN and graph attention networks. So yeah, not a lot of topics uh, were discovered in this week's lectures, but yeah, like they have some underlying math maybe uh, which I did not like cover, but yeah, which can be seen in lecture videos. And now like I was just preparing to like move on to some of the questions. So is this fine, Karpagam? Like, should we move on to the questions, or like should I like try to like revise? Okay, okay. So we can move on to the questions. So that's nice. Thanks. So so if you have seen the lecture, so would you like to attempt these questions, Karpagam? So like So the first question is which network neighborhoods are captured by the second and first order proximities in the line representation network? Like uh, like local or global, like so second order proximity captures like a local uh, local neighborhood or a global neighborhood. If you have an idea, would you like to attempt? Okay, you can recollect. Okay, you can't recollect. Okay, sorry. So, so note that actually, like, what was maybe I'll just in 2 minutes, again, like, I tell you like what are first order proximities and what are second order proximities. So, first order proximities in the line network are essentially the nodes which are directly connected to each other. So, if you and we have a direct edge with each other, then that's what we are accounting for in first order proximities, like the nodes which are directly connected to each other. Whereas in second order proximities, what we are accounting for is so let's say there are two nodes U and V, which may be like not be directly connected to each other, but let's say they have a lot of common neighbors. Then also like this line network says that they should be like close to each other in the graph embedding. So first order proximity just says like first order proximity says that the nodes should be directly connected to each other. Like first order proximity says that if the nodes are directly connected to each other, then they should be close in the graph embedding, resulting graph embedding. Whereas second order proximity states that even if two nodes are not directly connected, but they have a lot of common neighbors, then also they should be like uh, close in the graph embedding. So this is the high level idea of line representation network. Yeah. So you're saying first order is local. Yeah, that's correct. Like so that's a good observation, Garpagam, because you're looking at directly the edges. Yeah, and second order could be global. Exactly, because you're looking at maybe like so the common neighborhood for these two edge for any two nodes, the common neighborhood can be the whole graph, right? Or can be a lot of nodes. So that's why second order is global, whereas first order you're just looking at like the specific neighborhood of a vertex. Like you're not looking at. Yeah. So this is exactly correct. So very good job, Karpanu. So first order is local and second order is global. So so answer is B, global comma local. Second order is global, first order is local. So since second order captures the common neighborhood between two nodes, it is somewhat of a global property. Whereas first order proximity only captures the directly connected pair of nodes and hence is a local property. Hence, option B is yeah. So yeah, so I understand your okay. I also understand why you wrote like second order could be global, like because again like this is not entirely global because we are not looking at the whole graph but just looking at common neighborhoods of two vertices. But like at least from these options, the most appropriate one is like if we are calling first order as local, then it would be like more appropriate to call second order as global because it's more global than first order, right? So yeah, so very nice, Karpagam. So let's move on to question two then. So which of the following statements about random walk based methods is true? So they are slow because, so note that, okay, maybe I'll just revise this also. This is also not too hard. So random walk methods, actually we use these random walks methods because they are indeed very fast. Like these random walk based methods are much faster than other methods, and that's why we kind of use them. So these methods are fast because you can do random walks in parallel from multiple nodes. So you can use like parallel computation, and like these random walks are like, and here even if there are some failed nodes, like you don't have to recompute everything from scratch. You only need to look at some failed nodes. So actually like random walks are faster, and they are fast because they can run random walk from multiple nodes simultaneously. Simultaneously because we can run random walks in parallel from multiple nodes. So yeah. So option B is actually correct. Option C, that they are only applicable to indirect networks, is definitely incorrect. You can have random walks in directed networks, and they do not capture local structures, is also incorrect because random walks indeed capture the structure of the network. So yeah. So option B is correct. So option B is correct. And this is a lecture form from the lecture. Because the lectures. Okay then. So maybe we can move on to the third question. So Karpagam, like if you have any doubt at any point of time, like feel free to ask me in chat, and like I'll try to answer it. Like don't wait for me to ask if you have any doubts or not. Yeah. So the third question is, in the network based on the line proximity system. Okay, Karpagam, I believe that this question is something you can answer, like because you are familiar now with first order and second order proximity. Like, option A says that BE has high second order proximity and FA also has high second order proximity. So let's look at like maybe, so we are looking at second order proximity. So we are looking at common neighborhood. So the common neighborhood for B, like, so the neighborhood for B is this D and F, whereas neighborhood for E is on B and A. So actually they don't have anything in common in the neighborhood. So Kalpagam, so is this correct? Like, what do you think? Like, is this BE has second order proximity? Is correct? Okay, so Kalpagam is saying DF has high second order proximity. So yeah, definitely like DF has high second order proximity because their common neighborhood is like same. Like DF both have like B and A as common neighbors. Note that similarly, like B and A also have high second order proximity because B's neighbor is like DF and E, and A's neighborhood is also DF and E. So DF as well as BA have high second order proximity. So yeah, so DF has certainly has high second order proximity. Second option is that, and EA has first order proximity. Note that EA is directly connected. So yeah, E and A are directly connected, so they'll definitely have high first order proximity. Sure, Kirpa, you can look into the lectures again, or like, but I think like from what I just described, also like you will, you have sufficient uh, idea to answer the question. So yeah, so B, since E and A have like direct edge, so they have like high first order proximity. So at least this option is correct. Like, and maybe let's see option C. So option C says that DF has high first order proximity. That's incorrect because D and F have not directly connected by an edge. So this statement is definitely wrong. And this says that FE has high first order proximity. So FE again is not directly connected by an edge, so it does not have high first order proximity. The only option correct is option B. So maybe I'll just write this. So since D and F have the same neighborhood vertices, that is B and A. So the neighborhood for D and F both is like B and A, or maybe like A comma B, A comma B. Hence, DF has high second order proximity. Also, since E and A are directly connected to each other, hence they have also, since E and A are directly connected to each other, EA has high first order proximity. So hence option B is correct. I'll just B is, yeah. And then fourth question says that in a graph convolution network with a depth of x, when applied to a graph GV, comma E, how many learnable weight matrices are required? So yeah, so maybe you can go through the lecture videos. Or I did not discuss this much, but you can go into lectures to understand this. But note that if the network has a depth of x, so note that with each depth you have to associate one weight matrix. So this kind of thing we discussed in the previous week when we were discussing about like layers in the neural network and all. So note that a graph convolution network with a depth of x means that the convolution network has like x layers. So if there are x layers, so each layer has like one weight matrix associated to it. So how many learnable weight matrices are there when there are x layers? So one layer has one weight matrix. So if there are x layers, then x learnable weight matrices are there. So it's really not too hard of a question. You just need to have an idea of like what do these definitions actually mean. So x learnable weight matrices are required since hmm, every layer is associated to one weight matrix and there are x layers. Yeah, so this is the answer. So I hope this makes sense to some extent. If it does not, like you can like ask me for follow. Okay, then we can move on to the fifth question. The fifth question is actually again like it's about like first order, second order. So for the link, so this is something which has actually been discussed in like previous weeks, and like this is somewhat related to what we discussed this time also. For the link prediction task, which proximity measure should be considered? First order proximity or second order proximity? So what was link prediction? Let me just remind you again. So what link prediction was, suppose you are given two vertices U and V and you have to predict whether there will be an edge between them in the future or not. So which proximity measure would work here? So actually, Karpang, first order won't work here because you are actually, so what is first order proximity measure? In first order proximity measure, you are saying that, okay, if two edges have an edge between each other, then you say that they would be, uh, then they would be like, then they would be first order proximate to each other. But we don't know here, like if there is an edge between U and V. In the link prediction task, exactly this is the task at hand, that we have to predict whether there will be an edge between U and V or not. If you already knew if there is an edge, then you could talk about like first order. But since you don't know, you have to predict whether there will be an edge. So actually, you can use second order link prediction here, because you can say that, okay, if there are two vertices present, and if those two vertices have many common, uh, so this was covered actually in link prediction. Like if there are two vertices and if they have like common neighbors, then it's very likely that U and V will form an edge between themselves in the future. Yes, exactly. We do not know before, so it is second order. Like if you review the like maybe the link prediction lectures also, you will realize that this was actually also discussed in the lectures. Like if you and we have like a lot of common neighbors, then there is a very high chance that you and we will form an edge between themselves in the future. Like this was discussed in community detection, in link prediction, like in a lot of lectures. So yeah. So if nodes U and V have a lot of common neighbors, then it is likely that uh, an edge will form between U and V in the future. Hence, second order proximity can be used for link prediction task. So yeah, so second order proximity is correct. So what I really like about at least this line network is like although it's a very sophisticated and it's a like really nice network given in 2015, it just uses ideas which we already know from past, from like community detection or like link prediction and so on. So these first order proximity and second order proximity are not very new ideas, but just this mathematically formalizing all of these things is what this line network does, and that's why it's successful. So yeah, just a side comment I wanted to make. Okay, so then we have the sixth question that for the given graph, give one depth first search walk and one breadth first search walk. So maybe I can just do this myself. So so how do we do a depth first search walk? What we do is when we go to a node, uh, uh, we just go to another unvisited neighbor of it, and we keep doing this. So one DFS walk which can be done here is uh, kind of like this, that okay, you start at node 1. So suppose you start at node 1, then you move to node 3. So then you move to node 3, then you move to node 6. But after moving to 6, actually you realize that okay, like you cannot move any further. So you come back. Okay, I'll have to mute myself for a minute, Karpagam. Like I'll be back in a minute. So uh, just a minute, sorry. Yeah. Hi, sorry. So what you do is so you start from, let's say, this vertex 1, then you move to 3, then you can move to this vertex 6. But now you cannot move any further, so you come back to 3 and you see that still you cannot move any further. You come back to 1 and you can see now you can now move to this vertex 2. So you move to this vertex 2, let's say, and now again you have a choice of moving between 4 and 5. Let's say you choose this vertex 5. So you move to 5 and then you cannot move any further. You come back and then you see you can move to vertex 4. So yeah. So this is one example of a DFS walk. So note that one thing I want to, okay, maybe I'll point to about it later. And now let's just see one BFS walk. So BFS walk. So in BFS walk, what we are going to do is first let's say we visit 1. Then we need to visit these two vertices, like the vertices which are unit distance away from the vertex 1. So these are 2 and 3. Let's say we visit 3 once first, and then this vertex 2. Then we need to visit these three vertices. So let's say we visit 6, 5, and then 4. So something like that. So these are like examples of BFS and DFS walks. So one comment which I want to make is note that this is not the so these are not unique walks like actually so this is so these DFS walks and BFS walks are not unique. It's not that so actually like okay so let's just take example of DFS walk. So from 1 I first went to 3 and then went to 6. Another DFS walk could have been from 1 I instead went to this 2. So this 1, 2, 4, then 5, then 3, then 6 would also be a valid DFS walk. Similarly, in BFS walk, after going to 1, I chose to go to 3 and then 2. But since since both of these are unit distance away from 1, like I could have very well chosen to go to first 2 and then 3. So 1, 2, 3, 4, 5, 6 would also have been a valid BFS walk. But I just chose to wrote it as like so this is also valid, but that 1, 2, 3, 4, 5, 6 would also be valid. So I just want to point out that uh, uh, that BFS and DFS walks are not unique. There can be multiple DFS and BFS walks. So for example, here also, like there can be multiple walks. Okay then. So if this makes sense, then maybe we can move on to the last question for the day. So the last question is, in the context of node-to-vec algorithm, when the return parameter denoted as P uh, is set to a relatively high value. So like I already said that, so what effect does this have on the behavior of the random walker in terms of neighborhood exploration? So I think we already discussed this that in the node 2 actually return parameter determines how far random node is to explore from the source node. A high value of P indicates that random walker is more likely to move away from the source node. So higher the value of P, more likely is that you are going to move away from the source node. So in the seventh question, so higher the value of P, more likely. So if you set it to be relatively high value, then you are more likely to move away from the source node. So it primarily directs the random walk to focus on the local neighborhood emphasizing nearby nodes. So this is not correct. Like actually higher value of P focuses on far away nodes. It predominantly encourages the random walker to venture into the global neighborhood, broadening the scope of exploration. So yeah, so this is what's happening. Like it ventures into nodes which are far away from the uh, source node, and that's why you are venturing into the global neighborhood rather than the local neighborhood. It facilitates a balanced exploration between global and local neighborhood. So this is not done because you are setting P to a relatively high value. So you're exploring far away nodes. So you're not balancing between global and local. You are focusing more on global. And it effectively inhibits the random walker from engaging in any form of neighborhood exploration. So this is definitely incorrect. Like this is not what does one does in random walk. So option B is correct. So option B is correct. And this is just from discuss what is discussed in the lecture. So yeah. Okay. So Karpagama, I guess this is it what I had for the day. So if you have so I guess we finished a bit early. Do you have any doubts or any comments for today's session or something like you can ask and like we can have a discussion for 5-10 minutes. And also, like, I just want to point out that uh, initially I told you that I was having some difficulty in uploading. I remember, I think the week 9 lectures, I had some difficulty in uploading them, but I was finally able to upload them. Like, if you see now, the week 9 lectures are available, the week 9 session and the week 9 PDF. So week 8 is still pending because we did not have, week 8 is still pending because we did not have any session for that. So it is very likely that uh, Like we will not be having any live session for week 8, but I'll just upload some kind of a recording by tomorrow or day after tomorrow. Uh, because I don't think we can have a session for week 8 now, since now we are into like further weeks. But I'll still like uh, upload for upload a recorded session of week 8 so that people who have doubts from that week can still watch that week and like practice some problems and yeah, understand some concepts. Okay, so Karpagam is typing something in the chat. Oh, that's really nice, Karpagam. Good job. If you got full marks for most time. Like, yeah, I believe like if one is consistent in these sessions and pays attention to the question, like the question, the assignments are somewhat similar and yeah, can be done if these sessions, if you attend these sessions. So yeah, so good job, Karpagam. Yeah. So if you don't have any doubts for today, then I guess we can call it a day. So once again, thanks a lot for joining the session, Karpagam, and to everyone who's watching on YouTube, thanks a lot for watching the session. So hopefully I'll see a few more guys in person in the next session. So yeah, same timing like Monday 6 to 8 p.m. next week. So, and also like I believe in the meantime I'll upload a recording of like week 8. Like I'll record a session of week 8 lectures or something and just upload it. I don't think we'll have a live session, Karpagam, but I'll just upload a recording on YouTube recording and make it available to you guys. Okay then. So yeah, so thanks a lot for joining, and I guess yeah, uh we'll meet next week, Karpagam then. So yeah, you can leave the session. Thanks a lot. Bye bye.